Hi, Lingesh.
Sir, hi sir. Good evening, sir.
Good evening, Lingesh. Thank you so much for joining us today.
Sir,
No, thank you so much, Lingesh. நான் கேட்ட உடனே accept பண்ணதுக்கு.
sure,
And
sir.
no, I think the students will be largely benefited by your lecture. I'm also interested to know, look at what you're presenting. I mean,
Yeah,
maybe first time I'm going to listen to you.
sure, sir. Yeah,
Okay, pa. Best wishes, Lingesh.
yeah.
Do well. Thank you, pa.
Thank you, sir. Thank you.
Ah.
Okay. Good evening, students, and I would like to thank my guru, Dr. Gulam Alsad sir, for this wonderful
Lingesh,
opportunity.
sorry for the interruption.
Ah, yes, sir.
Maybe there is a formal beginning for this.
Okay. Sure, sir.
Um,
Yeah, we'll
maybe
go ahead with this.
Monish.
Yeah.
Yes, sir.
Monish, can we start, Monish?
Yes, sir. Sure, sir.
Yeah, yeah. Okay. Thanks, pa. Go ahead.
We'll be basically introducing you. That's what. So let's start the session. Good evening, everyone. It's a pleasure to welcome you to today's session on frequency selective surfaces. We are extremely honored to have with us Mr. Lingeshwaran Murugasamy, an assistant professor at St. Joseph College of Engineering with a Qualcomm certification in 5G technologies. With extensive experience in cutting edge tools like vector network analyzer and anechoic chamber, and notable research published in IEEE journals, he brings invaluable insights to our workshop today. His expertise, especially in shielding techniques and frequency selective surface designs, which we'll be learning today, makes him the ideal guide to navigate this complex topic. We look forward to a session filled with knowledge and practical understanding. Thank you for your time, sir. Thanks for joining. Please enjoy the session, participants. Over to you, sir.
Yeah. Thank you, Monish. Thanks for such a warm introduction. So I would like to know the demography of the audience. Like, are you all from third year or are you pursuing your final year? So what is the
So,
actual demography? Yeah.
yeah, most of them are from third year, sir. Some of them are from second year, and we are across. We are from various colleges actually. The
Oh, this is
majority is
very
from
good.
CET.
Yeah. Okay.
Yeah.
Okay. Yeah. Thank you. Okay. Sorry. Yeah. Okay. Even before I begin, I would like to throw few questions to you. Later, I thought of kickstarting my presentation. Uh, so how many of you have done a course on transmission line? How many of you have done a course on transmission lines and wavegates, or transmission lines and RF systems, RF and microwave? Anyhow, RF and microwave, I believe you might be learning at you may learn at the probably seventh or eighth semester. Okay. Uh, what about transmission lines? Like people who have already studied transmission lines, can you raise your hand? So there is an option to raise your hand. So I'll get to know like how many of you are like comfortable with transmission lines. Yeah. Okay, good. Great, great. Okay. Yeah, good. So thanks. Okay, thank you all. Yeah, you can lower your hand. Yeah. Okay, great. So I believe a couple of you have some preliminary insight on transmission lines and wavegates. Can any one of you tell me like why do we need transmission lines and wavegates as a course in your electronics and communication engineering undergrad course? Any idea? Like what is the need for such a course? So you are already doing course on like electronic circuits, right? Electronic devices, isn't it? You would have studied microelectronics. Why do we need an additional course, transmission lines and wavegates?
So is it because it's electronics as well as communication, wherein transmission lines and waveguides come into the communication portion?
Okay. Okay, right. Okay, I believe like I'll throw some light on why do we need this course. Then I'll dive into my topic. Okay. See, if you consider low frequency circuits, right? So you can very well measure voltage and current, right? Then how will you find impedance? Impedance is simply ratio of voltage and current. So you'll be in a position to find out what is the impedance the moment you know voltage and current. Okay, this is like we are quite comfortable in measuring voltage and current at low frequencies. But the moment you go for high frequencies, for example, if you consider 1 gigahertz signal or 10 gigahertz signal, right? So at those frequencies, if you measure voltage and current, you will get unreliable values because like the phase of the voltage and current will be varying at each and every point in your circuit, making voltage and current measurements completely unreliable. So that is why people use a different set of parameter called S parameters. Like if you want to understand frequency selective surfaces, there is a need to know S parameters. Okay, without some preliminary idea on S parameters, it will be quite tough to understand FSS or any high frequency domain, antennas, frequency selective surfaces. You can take any even oscillator design, amplifier design, right? Even filter design. Okay, if you take any high frequency structure, if you're not like comfortable with S parameters, it will be like slightly tough to know. So what is the key takeaway? It is very simple. In case of low frequencies, you can measure voltage and current. So the moment you know voltage and current, you can calculate impedance like Z equal to V by A. We are quite happy with it. What about high frequency? In case of low frequencies, voltage and current are measurable. At high frequencies, it is quite tough to measure voltage and current because at high frequencies, phase will vary at each and every point in your circuit. So you can't measure voltage and current reliably. That is why people use people use different set of parameters. Okay, it is nothing but S parameters, scattering parameters, right? So have you all studied H parameters? Probably to characterize a BJT or FET, you would have studied H parameters, hybrid pi model, isn't it? For any two-port network, right? So if V and I are not measurable, you can't use Z parameters, right? So Z is nothing but ratio between voltage and current. If V and I are not measurable, so you can't actually come up with Z parameter. So you have to use S parameter, right? So at high frequencies, voltage and current are immeasurable. We are using S parameters, right? So is it okay? Shall I proceed, students? Yeah,
Yes, sir.
yeah, good. Okay. Okay, so with this intuition, let me start my presentation. So this will like this won't be more of a formal presentation. So I'll be sharing my journey, okay, with FSS. Okay, so I started learning FSS probably in the year 2013 or 14, mid of 13 and 14, when I was doing my post graduation at SSN. So I did preliminary work on like frequency selective surfaces for shielding GSM 900 and 1800 signals. So let me get started with this presentation. Okay, so long back I utilized this presentation. Okay, yeah, I'll directly go here. So let us answer this question. What is a frequency selective surface, right? So this is basically a periodic surface, right? If you take a basic PCB structure, right? So you'll have, if you take a like basic PCB structure, you'll have a substrate, right? You'll have a dielectric material. So on top of the dielectric material, you'll have metal layer, and below the dielectric material also you'll have a metal layer. So here we are actually taking a single layer PCB with one metal layer and one dielectric layer, right? So you are having one dielectric layer. On top of the dielectric layer, you have the metal layer. So now we are actually going to have some kind of pattern that is being printed on that particular top metal layer. Okay, that metal layer will be etched to have some identical patterns. Okay, so that will behave
Sir,
like either band pass or band stop filter.
excuse me, sir.
Yep, sure.
Sorry
Oh,
to interrupt.
yeah, I'm not sharing the presentation. Yeah,
Oh, okay, sir.
yeah,
Just wanted to confirm that.
yeah. Sorry about it. Yeah.
Yeah.
Okay. So I believe my presentation is visible to you. Yes.
Yes, sir.
Yeah. Right. So let us answer this question: frequency selective surfaces. Right. So this is basically a periodic surface. Okay, you'll have identical elements, right, that are arranged in either one or two dimension. So probably if you take x and y, so along x and y you'll have identical elements, okay, that are arranged to form a grid-like structure, rectangular grid-like structure. Okay, so this will act as a spatial filter, right? Say I have two antennas, for example. Let me take this plus, yeah, PDF. So I believe my screen is visible to you. Yes.
Yes, sir.
Yes, it's
Yeah.
visible.
Yeah. So see here, I have two transmitting horns that are connected to a vector network analyzer. So this is the device used to characterize frequency selective surface, right? If you want to measure S parameters, ultimately you need a vector network analyzer. Okay, right? So here, this is basically a two-port device, right? So to one port I have connected the transmitting horn, and to the other port I have connected a receiving horn, right? So now I'm trying to eliminate this structure, okay, like using the EM signals from the transmitting horn. The moment I do that, right, some portion of the incident electric field will be reflected back, okay, right, and some of the incident field will actually go through the FSS and it will be received by your receiving horn, right? So now, based on the transmitted and received power, your vector network analyzer can compute the S matrix, right? So your S matrix, right? For example, if it is a two-port network, so the number of entries in the S matrix will be like, it is basically a matrix, right? So this is port one, this is port two. So probably for a two-port network, the size of the S matrix will be 2 by 2. So there will be four elements, right? So if you take, right? So if you take a two-port network, the size of the S matrix will be, it will be basically 2 by 2. Now what are the elements? The elements will be S11, right? So this is in subscript, S12, then S21 and S22. So these are the elements that will be present in the matrix, right? Okay, so S11, this is basically the reflection coefficient at port number 1. S22, it is the reflection coefficient at port number 2, right? So S21, so this is the forward transmission coefficient, this is the reverse transmission coefficient, right? So S11, reflection coefficient at port number 1, S22, reflection coefficient at port number 2, S12, what is S12? Reverse transmission coefficient, okay? This is the forward transmission coefficient. Clear? So what is S11? So S11 or S22, they basically represent reflection coefficients. Okay. Right? At port 1 and 2. Then if you take S21 and S12, they're all transmission coefficients. Right? So are we good to go with this?
Yes, sir.
Okay. Right? So we'll be measuring these parameters from vector network analyzer. Right? Okay. Once you do that, you can say whether this structure is able to either block the EM waves that are traveling through it, right? Or the structure can even design to be transparent to the electromagnetic waves. There are two possibilities, right? So either the structure can actually reflect the incident wave or it can allow the EM waves to travel through the FSS, right? Clear? So if it is reflecting the incident power, I call it as a band stop filter, band stop structure, right? If it is reflecting the incident power, I call it as band stop filter. If it is allowing the electromagnetic signal to travel from transmitting horn to the receiving horn, if the structure is transparent to the electromagnetic wave traveling from transmitting horn to the receiving horn, I call it as a band pass filter. Okay, clear? Shall I proceed?
Yes, sir.
Yeah. Okay. Right. So that is why we give this name. It is not an electric filter, right? So you have studied simple RLC and RLC circuits in series and parallel combination, right? So they basically come under the category of electric circuits. Here we are dealing with electromagnetic wave, right? So from one antenna, you'll have your electromagnetic wave, right? So say I have these two antennas. So now from this antenna, I'll have an EM wave, sorry, traveling from transmitting horn to the receiving horn. So frequency selective surface will effectively either reflect the incident wave or it will allow the incident wave to pass through. Okay. Okay, right? So you can either have, right, reflection or transmission, right? Once again, this will be a function of frequency. That is what we need to know. It won't allow all the frequencies to pass through. That is why I have given the name band pass or band stop. Some set of frequencies. The moment I say band, right, you'll have lower and upper cut of frequencies coming into picture. Okay, right? So see here, this is basically a 2D grid, right? So we have a 2D grid. This is along X, right? And this is along Z. Okay. So we have a 2D grid along X and along Z, right? So this is a XZ plane. So where I have identical elements that are deployed. So now you can see there is a finite distance between each and every element along X, right? Dx. Then along Z direction also you have finite distance between each element, right? Okay, so the structure is entirely, if you look at the structure, right? So you can very well say this is a identical structure, right? So all the elements are identical and they are all separated by uniform distance along X and along Z, right? So now this is the incident field, right? This is the incident electric field. Okay, say this is emanating from a transmitting horn, right? So EA is the electric field intensity, right? So I have already told you this structure can either reflect the incident field or it can allow the electric field to pass through. So you'll have reflected electric field and you'll have transmitted electric field. If you know what is the electric field intensity with respect to incident field, transmitted field and reflected field, so you can like come up with few parameters which are used to characterize your frequency selective surface, right? So these are the parameters that are used for evaluating frequency selective surface. Okay. Number one, reflection coefficient, right? So as I have already mentioned, right, reflection coefficient, it is simply ratio between reflected electric field intensity and incident electric field intensity, right? So if you want to use S parameters, right? So this is field, electric field. Naturally, it becomes 20 log of what is the reflected electric field intensity and what is the incident electric field intensity. Clear? So reflection coefficient deals with ratio between reflected and incident electric field intensities. What about transmission coefficient? It deals with ratio between transmitted and incident reflected transmitted and incident electric field intensities. You can also use power notion. If you use power, this will be simply 10 log. Okay, right? So whenever we deal with reflection coefficient, it is ratio between reflected and incident electric field intensities. What about transmission coefficient? Ratio between transmitted and incident electric field intensities. Clear? Shall I proceed? Yeah? Students?
Yes, sir.
Yeah. Right. So these two parameters can be used interchangeably, right? Shielding effectiveness, this is nothing but minus S21 in dB. So if you know what is your transmission coefficient, right? So if it is minus, for example, if it is minus 20 dB, shielding effectiveness will become plus 20 dB, right? So these are the major parameters that are used to characterize the frequency selective surface, right? So number one, reflection coefficient. Number two, transmission coefficient. So if you study in any standard literature, these are the parameters you will generally come across. Okay. And one more parameter, this is called figure of merit, right? This is the major figure of merit. Okay. So what is the dimension of your unit cell, right? So see here, if you take a frequency selective surface, I have already told you. So this is basically a rectangular grid with identical elements, right? So this is a rectangular grid, okay, with identical elements. It is not necessarily rectangular. You can this could also be a square, okay. Generally, if we design, we will always have it as a square, okay, right? So in theory, like they would have actually considered infinite plane size. In reality, we won't have infinite size, right? We'll have a limited size, okay. We'll have a, for example, 1 feet cross 1 feet, okay. That would be the dimension used for fabrication, right? So we'll have large number of unit cells, right? They are, see here, they are all identical to one another, okay. This one particular segment, I call it as a unit cell. So now this is basically a 3 cross 3 array. If you look at this, how many unit cells are there? Any idea how many unit cells are there? How many elements are there? 3 by 3 in the sense? So there
9
are
elements.
9 elements. Yeah, very good. Okay, right. So what are the parameters used? So reflection coefficient, transmission coefficient, shielding effectiveness. We are good with that. We are good with these 3 parameters. What about figure of merit? See, as I have already told you, right? If you look at this, there are 9 unit cells. Each of them are separated by a finite distance. And this distance will almost remain the same. Okay. Right? They're all equidistant. Right? Along mostly most of the structures it will be like equidistant. But there are a few structures, okay, where this particular inter-unit cell distance will vary. Okay. Along X and Y, here they have used the axis Z. Okay. So what about figure of merit? So figure of merit, it is simply the comparison between size of the unit cell, okay, with respect to the electromagnetic wave, what you are actually trying to either shield or if you want your surface to be transparent to that particular EM wave, okay. So from that particular frequency, what you can do, for example, if I want my frequency selective surface to shield GSM 900 signal, what about your carrier frequency? Your carrier frequency will be somewhere around 900 megahertz, right? Say I want my frequency selective surface to stop this electromagnetic signal, electromagnetic wave. Now what I can do, from this frequency, I can estimate what is lambda. What will be lambda? For a 900 megahertz signal, lambda is equal to C by F, isn't it? So C is nothing but velocity of your EM wave in free space or vacuum. It will be 3 into 10 power 8 meters per second. And what about frequency? Frequency will be 900 megahertz, nothing but 9 into 10 power 8. Am I right? So 10 power 8. So this will reduce to the form 1 by 3. Am I right? So 1 by 3, nothing but 0.33. Okay, right? This is meters. 0.33 meters. 334 meters. So if you convert that into centimeters, right? So it will be 33.4 centimeter, right? In most of the commercial simulators, whatever we use for simulating frequency selective surfaces, the dimensions are generally measured in millimeters. So if you convert this to mm, it will be 334 mm. So whenever you design a frequency selective surface, right? So that frequency selective surface will be like, it will be much less than this particular value. For example, if it is 334 mm, the value of lambda is 334 mm. Whenever you design a frequency selective surface, right? So that structure should be miniaturized compared to this wavelength. Okay, only then the structure will exhibit stability with respect to different angles of incidence, right? Your electromagnetic wave can come from any angle. Okay, if you want to have stability with respect to different angles of incidence, right? Ultimately, you want to have miniaturized unit cells. That is only possible if you reduce the unit cell dimension much below your wavelength. Okay, clear? Right? So this figure of merit is simply comparison between what is your original wavelength corresponding to the electromagnetic signal, what you're actually willing to shield, okay, and P is basically the unit cell dimension, right? So this is the wavelength corresponding to the 900 megahertz signal, and if you design a frequency selective surface for that, what is the size of the unit cell? P is basically periodicity, right? Okay, so this parameter P ultimately represents periodicity of your unit cell. Shall I proceed? So can any one of you tell me what are the parameters used in evaluating FSS? Reflection coefficient, right? Ratio between reflected and incident electric field intensities. Transmission coefficient, ratio between transmitted and incident field intensities. Then shielding effectiveness, nothing but minus of S21 in dB, right? If the value of transmission coefficient is minus 20 dB, then shielding effectiveness will be plus 20 dB. Okay. Then what about figure of merit? Figure of merit, it is simply the ratio between wavelength and size of your unit cell. Okay. Clear? Are we good to go?
Yes, sir.
Yeah.
Yes, sir.
Right. See, whenever you study any technical literature, okay, like if you study textbooks on frequency selective surfaces or any IEEE articles, there are two major categories, right? So one will be dipole array, other one will be slot array. So what is the general idea here? So here, if you look at these two structures, right? So see here you have only these are metal elements, okay, right? These are all metal elements, okay. So I call it as dipole array, right? So these are all metallic elements which are separated by finite distance, okay, along x and y, right? So this structure will provide band stop response. Okay, this will act like a band stop filter. And what about this? If you have a metal sheet, if you cut out slots, okay. Say I have a large metal sheet, I have cut out slots, right? So whenever I cut out slots, right? So I'll get some portion of the metal, right? So that is actually available here. I can call this as a complementary structure, but if you try to simulate that, the response won't be complementary. Okay, there are few more parameters that will decide the response. But what is the key takeaway? If you have freestanding metallic elements, right, the frequency response will be like it will be similar to band stop filter. And if you cut out the slots, these are basically slots cut out on a large metal sheet, right? If you cut out slots, right, the entire structure, if you put horn antenna on both the ends, this structure will behave like a band pass filter. Okay, this will be transparent to the electromagnetic wave, but if you have this kind of freestanding metallic elements, this will reflect the incident EM wave. Okay, right? So this will reflect the incident EM wave. This structure will allow EM wave to pass through. Are we good to go? So there are two major categories. So one is dipole array, other one slot array. In dipole array, right, you'll have freestanding, or you can also have metallic elements available on a dielectric substrate. Okay, right? In both categories, it will serve as it will behave like a bandstop filter, right? The incident EM field will be reflected. And what about the other category? If you have a large metal sheet and if you cut out the slots, right, this will become a transparent structure. Okay, right? All the incident EM waves will be allowed to pass through, right? So once again, you need to know this is once again band. Okay, here I'm mentioning band. Whenever I mention band, you'll always have lower cutoff and higher cutoff frequency, right? So if you take GSM 900 signal, can any one of you tell me what is the lower and upper cutoff frequencies? GSM 900 popular band. If you don't have any clue about the bands, right? Actually, I'm heading 5G and 6G Technology Innovation Center in my campus. So there is a beautiful site on 5G. It is NR explained, right? So you can go to this particular site, right? So here you see frequency, AR, FCN, and operating bands, right? So I'll share this in the chat. Okay. So I believe I'm audible to you. Yes.
Yes, sir.
So see here, like if you want to look at the frequency bands, right? So it is clearly given here. Okay. Right. Yeah. So this is the band what we are actually targeting. For example, if it is N8 band, right? So 880 to 915 megahertz, right? So this is the uplink band, downlink 925 to 960. Okay, right? In mobile communication, you very well know, right? So uplink frequencies will be lower than downlink because all the mobile phones are battery operated. You want to conserve power, right? So high frequency signals, they encounter high attenuation through air, right? So that is why in mobile communication we always use low frequencies for uplink, right, and high frequencies for downlink, right? If you take base stations, right, power is not a major metric, but when it comes to mobile, you want to conserve power, right? You want your battery to you want your mobile phone's battery to stay alive at least for a day long, right? So that is only possible if we do this kind of frequency planning. Okay, yeah, let us get back to our business. So see here, so for all the frequency bands in 5G, you can see what are the uplink and downlink bands. Okay, so this is the band what we were actually targeting, right? So 880 megahertz, that is the lower cutoff frequency in uplink, and 915, that is the higher cutoff frequency in the uplink. This is the lower cutoff, this is the higher cutoff with respect to uplink band. And what about DL with respect to downlink? This is the this is the lower cutoff frequency and this is the higher cutoff frequency, right? So if you want to design a frequency selective surface for GSM 900, so this is supposed to be a dual band structure. Okay, one for shielding your uplink and the other one for shielding your downlink. Okay, right. Right. So in all the technical literatures, you'll either find band stop or band pass response, right? So if you have dipole array behaves like a band stop filter, and if you have slots cut out on a metal sheet, it will behave like a band pass filter. Okay, right. So what about the elements, right? So what are the possible choices? Okay, I have already told you in case of FSS, right? So FSS, frequency selective surface, is basically a grid-like structure. Okay, say this is X, right? Say this is X and this is Y, right? So I'll have identical elements along X and Y, right? So now the question here is, what should be the structure of each element, right? Okay, so we have already, like, we have the clarity that all the elements are identical. Now the question here is, what about the element shape, right? Is it necessary to have only dipole like structure? It is not necessary, right? You can have center connected elements, right? You can have center connected elements, right? And you can also have loop type elements. So see here, this is the only metallic portion. Okay, the central region is actually now cut out. Have a look, this is a square loop. And what about this structure? How many sides are there? 1, 2, 3, 4, 5. How many sides are there? Hexagonal loop. Okay, circular loop, right? So this we call it as four-legged loop, four-legged loaded loop, right? It's a tripod element. So there are so many loops that are available, okay, right? And group 3 here, you can have solid interior, right? You can use either square patches, circular patches, or hexagonal patches. Okay, apart from center connected or loop type or solid interior elements, we can also use combination of all this, right? So you can actually, for example, if you see this structure, they have taken this particular structure, okay, right, and somehow they made it look like a loop. Clear? So you can combine any of these elements to come up with the unit cell structure, right? So different categories are there. Either you can have center connected elements or loop type elements, or you can have solid interior elements, or combination of any of these elements, right? You can also have fractal structures, right? If you study the literature, right? So fractals were explored to a great extent for design of miniaturized antennas and frequency selective surfaces, right? So that is what we are going to see in the subsequent slides. So I believe we are good to go with this introduction, right? So a quick recap: in case of frequency selective surfaces, you'll have identical elements along x and y. This is basically a spatial filter. Okay, just like electric filters, okay, dealing with your electrical signal, this is a spatial filter dealing with electromagnetic waves, right? Right? What are the parameters we see here? We see only S parameters, because at high frequencies you can't measure voltage and current, right? So we only have S parameters. So S parameters are nothing but
Participants, please hold on. Sir is having some network issue. He will join shortly.
okay. Sorry, students. There is a small, like I had signal outage from my end. Okay. So I believe my screen is visible to you. Yes.
Yes, sir.
Yeah. Okay. See, if there is any like outage, kindly let me know. Okay. If you're not able to perceive what I'm uttering, kindly let me know. Right. So I have discussed the parameters that are used to characterize a frequency selective surface, right? And different categories, right? So in any technical literature, okay, you'll either come across frequency selective surface providing band stop response or band pass response. Okay, right? So what are the different choices available for use as a unit cell element? You can either have center connected elements, or you can have loop type elements, or you can either have solid interior elements or combinations. So there is a beautiful textbook on frequency selective surfaces authored by Ben A. Monk. Okay, when I was actually going through the textbook like 10 years back, uh, actually the author, he has expressed his love for loop type elements. So that made me to dig deep. So most of, like if you take most of the work whatever I have done so far, like all of them are like they are all falling under loop type elements. Okay, right? So that is the kind of love I had on frequency selective surfaces textbook by Ben A. Monk. Okay. Oh, we can actually call him as father of frequency selective surfaces. Okay. So that is the amount of work he has actually done in this particular domain. Right. So for sake of time, I'll be skipping this particular literature review. Right. Uh, yeah, let us bounce back to our discussion. Say I want to design a frequency selective structure for GSM 900 band, right? So I have already told you this structure has to be dual band, right? So you will have uplink and downlink. Okay. So why downlink frequencies are higher? See, like if you take your mobile, right? So this is your mobile and you have a base station here, right? So your uplink frequency will be always lower because frequency and if you take received power, okay, right? So if you take frequency and received power, they are inversely proportional to each other, and this is what you have to know, right? So it is received power is inversely proportional to frequency square of your frequency, right? So larger the frequency, right, smaller will be the received power with respect to distance. Okay, this is basically path loss. Okay, right? So that is why all the cellular service providers, they'll always use, right? So this is actually nowadays if you take 5G, the standard is now dictated by a body called 3GPP, right? So 3GPP, like if you look at the standards, right, the uplink will be always lesser. Okay, if you take any standard, right? So here, in case of mobile communication, right, uplink will be lesser, downlink frequency will be higher. In case of downlink, there is no power issue, right? So your G node B, this can actually like pump the power and it can overcome the path loss, right? Okay, there are a lot of closed loop power control systems that are available. Okay, I don't want to take my discussion away from frequency selective surfaces much in deep into communication. Okay, so let us confine our talk only to frequency selective surfaces, right? So if I want to design a frequency selective surface for GSM 900 band, right? So there has to be a dual band. The structure is supposed to be a dual band structure, right? So you have to tackle uplink and downlink frequencies, right? Okay, now I have a double square loop, right? So one square loop will take care of uplink and the other square loop will take care of downlink. Can any one of you tell me which loop, whether the inner loop or outer loop, which one will take care of high frequency? There is downlink. Which structure will take care of downlink? Students, anyone?
Sir, will it be the inner loop?
Yeah. So high frequency in the sense, for example, see here, high frequency in the sense, right? So frequency and wavelength, they are all inversely proportional, right? So downlink frequency will be higher, right? So frequency and wavelength are inversely proportional to each other. So now whenever I have high frequency, wavelength will get shortened. Okay, right? So this structure will take care of downlink, basically your high frequency, and the outer one, right? The outer square loop will take care of your uplink. Okay, right? And instead of PCB here, I have used paper as a substrate, right? So why did I go with paper instead of a regular PCB structure? So paper, this is basically a flexible substrate, so you can utilize it on any structure, right? So if you have a irregular geometry, right, if you want to cover some irregular geometries, you can basically use paper. Being paper being flexible rather than a rigid PCB, you can use paper, right? So this is the dielectric constant, right, 3.4, and loss tangent. uh, Guys, can any one of you tell me what is loss tangent? You have done a course on electromagnetics, right? Loss tangent. So have you all studied Maxwell equations? Ampere circuit law and Maxwell's correction to Ampere circuit law. Yeah, anyone? What is del cross H? I believe you would have done a course on electromagnetics. What is del cross H? So what is del cross H, students? Yes, anyone? Del cross H?
So which is J plus J, uh,
Yeah. So
it's a
Ampere
current
circuit
density
law, yeah, exactly. Del cross H is J. This is
plus
the equation given by Ampere. Then some
J omega
improvement
mu
was actually
epsilon
done. Yeah, exactly. Yeah. Go ahead, tell. Yeah.
J omega mu epsilon dou E
Okay.
by dou T, sir.
Yeah. So let me use a differential form. Okay. Right. So del cross H equal to J. Right. So this is basically your Ampere circuit law. If you take any circuit, right? So if you want to know what is the magnetic field, okay, available in this particular loop, that will ultimately depend on what is the current density. Okay. Del cross H equal to J plus dou D by dou T. This is the correction made by Maxwell, right? So you can rewrite this equation, or let me clean it up. So del cross H equal to conduction current density, right, plus dou D by dou T, displacement current. Okay, this is nothing but sigma into E. So in phasor form, dou by dou T, like what he said, J omega, then D is electric flux density, right? So now that will become epsilon into E. Okay, nothing but electric field intensity, right? So now see here, so this is JD, right? If you find the ratio between these two, right? See why we are interested in loss tangent in a dielectric. If you take any dielectric, why we are interested in loss tangent? If you take any dielectric, okay, it won't remain as a dielectric for the entire frequency, right? And based on the amount of like field you apply, okay, there will always be a breakdown, dielectric breakdown. Okay, at some point your dielectric will even become a conductor. Okay, that is still possible, right? So loss tangent basically tells you to what extent a dielectric is a conductor. Okay, right? So ratio between these two quantities is nothing but loss tangent. Okay, so for any dielectric, loss tangent is defined to say to what extent the dielectric behaves like a conductor. Clear? So I believe we can bounce back considering time as a matter of fact. Yeah. So if I want to shield a GSM 900 signal, right? So I need two structures, okay, to take care of uplink and downlink. Instead, you can design a you can design a square loop having a larger width, right? Okay, so these are the side dimensions. So side length 46 mm, okay, for outer square loop. You can have a look at the width also. Outer loop is 2 mm wide, inner loop 2 mm wide, and the distance, inner loop distance, this particular distance, inner loop distance, it is 1 mm. These two loops are segregated by a distance of 1 mm. So I have used a paper as a dielectric, right? So the thickness of paper was around 0.5 mm. And if you look at the copper strips that are designed in this particular form, two square loops, the copper strips were around 0.05 mm thick. Okay, and the distance between this unit cell and the neighboring unit cell, it is around 1 mm. Okay, clear? So this is the structure of a dual band frequency selective surface that can take care of GSM 900 band. Okay, clear? Shall I proceed? So this is a 3x3 array. Can you see how many unit cells are there? Unit cell 1, unit cell 2, unit cell 3, 4, unit cell 5, unit cell 6, 7, 8, and 9. So 9 unit cells are there and they are all identical, right? So they are in the form of a grid, right? So I have this inner loop taking care of my downlink and the outer loop taking care of my uplink, right? Or I can say the outer loop having a larger dimension, right? So size is higher. What about frequency? Frequency will be lower. Okay, so this will take care of the lowest frequency. This will take care of the highest band. Okay, right? So this is your lower band and this is your higher band. Inner loop is responsible for shielding signals in the higher band. Okay, right? So see here, if you look at the surface current distribution, right? So whenever we discuss frequency selective surfaces, there are two more parameters that are to be discussed apart from these parameters, whatever I have discussed. Okay, right? Apart from reflection coefficient and transmission coefficient, you have to know two more parameters. Okay, one is polarization, right? So one is polarization. Okay, why am I interested in polarization? Guys, why am I interested in polarization? So say I have a antenna like this. Say this is my transmitting horn, right? This is my transmitting horn and this is my receiving horn. Okay, so this is my receiving horn. And the frequency selective surface is now deployed at the center. Okay, this is your FSS, right? So now your electromagnetic signals, right? Your electromagnetic wave coming from transmitting antenna, right? Traveling from your TX transmitting horn to the receiving horn, it can have any kind of orientation, right? Polarization is simply the orientation of the electric field vector, right? So if you take this particular horn antenna, right? So your electric field will be vertically polarized. If you rotate your horn, then your electric field vector will become horizontally polarized. Okay, so your electric field can be vertically polarized or horizontally polarized. So no matter whatever be the kind of polarization, I want the structure to provide same frequency response, right? Do you get the idea? So when what is the thumb rule for design of frequency selective surfaces? The structure should be polarization insensitive. The structure should be polarization insensitive, right? So whether a vertically polarized E field is incident or horizontally polarized E field is incident, the structure should provide same response. That is the first thumb rule for design of frequency selective surfaces. And the second thumb rule, okay, this there is no need to place the horn antenna like this. Your horn can be placed anywhere here, right? If you take the entire contour, okay, so your horn antenna can be placed anywhere on this particular contour. Then say I take these 2 points, right? Say I'm considering these 2 points. This is point 1 and this is point 2, right? So if I place the horn antenna, this will be the angle of incidence of the electric field vector. And if I place my horn here, this will be the angle of incidence, right? So there is no guarantee these two angles. It is quite evident that these two angles will be quite different, right? Am I right? So these two angles will be different. So now the structure has to take care of different angles of incidence also, right? Your electric field can come from any angle. Your structure should be in a position to tackle varying angles of incidence, right? So that is the second thumb rule. Clear? So thumb rule 1, whatever be the polarization or orientation of the electric field vector, I want the structure to provide same transmission response. Okay, that is thumb rule number 1. And thumb rule number 2, whatever be the angle of incidence, I want the structure to provide same frequency response. Clear? Are we good to go, guys? Please respond.
Yes, sir.
Yes, sir.
Yeah. Uh, I believe you are able to hear me. I just want to confirm whether you are able to hear me. Yes?
Yes, sir.
Yeah, okay. Yeah. So now let us try to address the first design challenge, whether the structure is insensitive to polarization or not. Okay, now let us take the vertically polarized E field. Okay, if you take the vertically polarized E field and if you allow one such electric field vector to pass through your structure, right, you can check what is the current surface current on your frequency selective surface. This is basically a unit cell, right? You can check the surface current distribution. If you check the surface current distribution for the incident electric field vector having vertical polarization, you can very well see, right, this portion is resonant. Am I right? If the electric field is, if the incident electric field is vertically polarized, okay, so let me erase all ink on the slide. If the electric field vector is vertically polarized, you can see, right, the higher current distribution on the vertical segments, isn't it? And what is the difference you spot for 940 megahertz, right? For a 940 megahertz. Okay. So here I have designed the structure to take care of GSM 900 and 1800, both bands, right? Now let us bounce back to this particular. So see here. So this is one such band, N8, and the other band, N3, N3 and N8. These are the two bands, okay, what we are actually trying to like cover. Okay, 882, here 882, 960, and here 1710 megahertz to 1880 megahertz, right? So to put it in simple terms, right? So I can say we are trying to shield GSM 900 and GSM 1800 signals, right? So 880 megahertz to 960 megahertz. So now this is my first band, band 1, and the other band, if you take the second band, I'm trying to address 1710 megahertz. From 1710 I want to cover this particular frequency, right? Okay, so here if you look at band 1 and band 2, right? So band 1, it is taken care by the outer loop. Band 2, it is taken care by the inner loop. Shall we proceed?
Yes, sir.
Yeah, okay. So now if you look at the surface current distribution, so see here, so this is your lower frequency, lower band. This is band 1. For band 1, the outer loop will be resonant. For band 2, the inner loop is resonant. Okay, just by looking at the current distribution, you can very well see. See, this current distribution is, you can see the current distribution on the structure because of the incident electric field. Whenever the electric field is incident on the metallic structure, that will excite the surface current on the structure. Okay, right? So we have used CST microwave studio. This is a like electromagnetic simulator. Okay, there is yet another tool called high frequency structure simulate HFSS. So I have used CST microwave studio to simulate to simulate the entire structure, right? So for a vertically polarized E field, I can very well see. So there are two dips, right? And if you look at minus 10 dB as a metric, right? I'm taking minus 10 dB as a metric, which states why do I take minus 10 dB as a metric? Any idea? If S21 is minus 10 dB, it indicates 90% of This is the portion under, these are the frequencies that are having S21 less than minus 10 dB, right? So this is my lower cutoff frequency, this is the higher cutoff frequency, right? You can very well see this covers the entire band. 880 megahertz, nothing but 0.8 to 960. Am I right? The entire band is being covered here. And once again, so here if you look at this, around 1.7, it is going all the way up. Okay, right? 1.8, more than 1.8. So we are able to shield both band 1 and band 2 with the help of this structure. Okay, why do we take minus 10 dB as a benchmark for S21? We'll do a simple math here. Okay, so I have already told you what is S21. So S21, it is simply ratio between, if it is, let us take power. Okay, for example, if I take power, it is the ratio between transmitted power and incident power, right? So now what is the value of S21? If the value of S21 is 10 dB, right? So 10 into log of PT by transmitted power divided by the incident power. So if you do the simple math, right? So this is a base 10 logarithm, right? So you'll have minus 1 equal to log of PT by PR, sorry, PT by PI, right? Then this will become 10 to the power minus 1 if you get rid of log. Okay, this will be ratio between transmitted power and incident power. So what is 10 power minus 1? Basically 1 by 10, right? So that is PT by PI, right? So what is the inference? So the inference is that PT will be, transmitted power will be PI incident power by 10. Okay, right? Or I can rewrite this as 0.1 times of incident power, right? Or I can say 10% of incident power, right? Transmitted power will be, right? So transmitted power will be 10% of the incident power. That is why we take minus 10 dB as a benchmark. So if you take minus 20 dB, any idea what will be the transmitted power? For example, if the value of S21 is minus 20 dB, right? What will be the transmitted power? If you do the simple math, it will become 10 power minus 2. Can very well give a try. So it will be 10 power minus 2. So 10 power minus 2 will be the ratio of transmitted, ratio between transmitted power and incident power, right? So nothing but, this is nothing but 1 by 100. Okay, this is the ratio between transmitted power and incident power. Okay, then if you do the rearrangement, so what will happen? If you do the rearrangement, it will become Pi by 100. So Pi by 100, how can I rewrite this? 0.01. Am I right? 0.01 times of incident power. Or I can say, or I can say 1% of the incident power. Right? See, if the value of S21 is minus 10 dB, this is case 1, right? In case 1, we have considered S21 as minus 10 dB. If we take minus 10 dB as a benchmark, I can say, what about the transmitted power? Only 10% of the incident power is transmitted from port 1 to port 2, from the input side to the output side. So what is the inference here? The inference is that remaining energy, you very well know energy can neither be created nor be destroyed. What happens to the remaining 90% of the incident power? 90% of the incident power, right? 90% of the incident power is reflected back. Okay. And what about this particular case? If the value of S21 is minus 20 dB in case 2, the value of S21 is minus 20 dB. From this math, we infer the fact that only 1% of the incident power goes to the output port. What happens to the remaining 99% of the incident power? Here 99% of the incident power is reflected back, right? So do you get the idea, students? So now you have to decide whether you want to design the frequency selective surface with a 90% reflection or 99% reflection, right? Whether you want 10% of the incident power to go to port 2 or 1% of the incident power to go to port 2. Clear? So now in most of my studies, I have taken minus 10 dB. Okay. If you want, you can also have minus 20 dB. Clear? Are we good to go, students? Shall I proceed? Yes?
Yes,
This is
sir.
such a silent crowd. Okay. So you have to decide whether you want to design a frequency selective surface with 10%, like whether you need 90% reflectance or 99% reflectance, or you can say 10% transmittance or 1% transmittance. It is up to you, right? Okay. So we have taken minus 10 dB as a benchmark, right? So I have already told you we are designing frequency selective surfaces for GSM 900 and 1800. So in that scenario, right? So band 1 is between 880 and 960 megahertz, taken care by the outer loop. And band 2, it is available between 1710 megahertz and 1880 megahertz. This is taken care by the inner loop. Okay. Right. Yeah. So now see here, from this plot, I can see two dips in the S21 plot, right? So these two are complementary, S11 and S21, right? So see here, if you take S21, I can very well infer the fact if I take minus 10 dB as the benchmark, I can draw a line like this, right? See, in case of amplifier characterization in your laboratories, you would have drawn a 3 dB line. Am I right? In order to find out if you have an amplifier, if you want to find out what is the frequency response of the amplifier, you would have used a like you would have used a uh, similar graph sheet to find out what is the 3 dB bandwidth, right? So from the mid band gain, right, you would have taken 3 dB beneath that. You'd have drawn a line, 3 dB line beneath that to find out what is the 50% operating bandwidth. So here, how to find the operating bandwidth? It is quite easy. We have taken minus 10 dB to ensure that there is 90% reflection in this particular band. Only 10% transmittance. Okay. So what is the lower cutoff frequency? If you take minus 10 dB as a reference line, so have a look. This is the lowest cutoff frequency in band. This is band 1. This is the higher cutoff frequency in band 1. Right? So 880 to 960, the entire band is now covered. Okay. And what about band 2? It is between 1710 and 1880. Right? So once again, the entire band is being covered here. Okay. So I can say now the structure can act as a shield for electromagnetic waves, right? That are centered around either GSM 9, this is your GSM 900 band, and this is GSM 1800 band. If you take any of these two bands, right, the structure can actually act as an electromagnetic shield. Okay, so what will be the amount of reflected power? 90% of the incident power will be reflected. Only 10% of the incident power will be reaching port 2 from port 1. Right? So this is with respect to horizontally polarized E field. If the incident E field is horizontally polarized, right? So you can see the horizontal segments of the square loop that are resonant with regard to the incident field, right? So at low frequency, you can see this the outer loop is resonant. At high frequency, the inner loop is resonant. Okay, right? And this is the S parameter plot. Okay, with respect to horizontally polarized E field, right? So you can take minus 10 dB as a reference. If you take minus 10 dB as a reference, we are getting the same response. The structure is able to provide shielding in the GSM 900 and 1800 band. So now you can compare. Okay, so if the vertically polarized E field is incident, what is the response of the structure, right? And you can also plot the response of the structure for the horizontally polarized incident E field. For both the polarizations, right, it is immaterial, right? For both the polarizations, right, the structure is providing same transmission response, indicating the fact that the structure is actually polarization insensitive. No matter whether vertically polarized or horizontally polarized E field is striking your surface, the structure's frequency response remains the same, right? So now the first thumb rule, it is satisfied, right? For both vertically and horizontally polarized E field, the structure is providing same transmission response. Now let us move on to the second thumb rule, right? So now the electric field can be vertically polarized, but it can come from any angle, right? The angle of incidence can be anything between 0 and 90 degree, right? So why am I saying it is 90 degree? Listen. So this is my transmitting horn. Okay, this is my transmitting horn antenna, TX horn. So I have the frequency selective surface in between. This is my FSS. And I have another receiving horn here. Another receiving horn antenna available here. Right? So there is no necessity to have a line of sight. Right? So you can deploy your horn anywhere here. Am I right? Okay. So here, if you take, this is the normal drawn to the surface. Right? This is the normal drawn to the surface. So here angle of incidence is 0. If this is the z axis, right? If you are if you are comfortable with the coordinate system, Cartesian coordinate system, theta is the angle measured from z axis. Okay. So you can deploy your horn antenna anywhere here. You can deploy your horn antenna here, right? So if I deploy my horn antenna here, right, somewhere here, now what will be the angle? This angle will be 45 degrees. Okay, right, with respect to the normal drawn to the structure, right? It can be 0 degree or 30 degree, 45 degree, 60 degree. It can even be 90 degree, but this is a grazing angle. Okay, generally it is not used. Okay, up to 75, 80 or 90, sorry, 75, 80 or 85, not more than that. Okay, this is a grazing angle. Okay, right? So clear? Why do we have incident angle limited to 90 degrees? So on either sides, you can also deploy your horn somewhere here also, right? See, this is for with respect to test setup. In reality, if you deploy your FSS, right, electric field can come from any direction, right? So the angle of incidence, anyhow, it is actually limited to 90 degrees. Maximum angle is 90 degree. So if you place in the line of sight, so it is based, right, it will be 0 degrees here. Okay, right, 0, 30, 45, 15, 30, 45. Okay, 60, right? 75. Gradually you can increase up to 90. Clear? Now we are going to investigate with respect to different angles of incidence whether the structure is providing same transmission response or not. Okay. Let me get back to the yeah. So see here, for vertically polarized E field, we are checking whether the structure is providing same response for different angles of incidence, right? So here we have investigated the transmission response between 0 degree and 45 degree, right? You can see a small shift, okay? A very small shift, right? So for different bands, GSM 900 and 1800, what is the resonant frequency? What is the attenuation? What is the amount of attenuation? Nothing but, so this is shielding effectiveness, nothing but shielding effectiveness. So minus of S21 in dB. So do you see the values greater than 20 dB, right? So all these values are greater than 20 dB, indicating the fact that not even 1% of the incident power is available at port number 2, okay, at the resonant frequency, right? See, one bottleneck, what I observed, if we use double square loop, right? If we use double square loop, whenever the angle of incidence increases, look at the lower band. We are not able to cover 880 to 960, right? Okay, so that is why. So we move to this particular band. Okay, we move to this particular structure. So this is a modified double square loop. Okay, we have retained the outer loop. The in case of inner loop, okay, we are using a convoluted structure, right? So we are using a convoluted structure in order to miniaturize the unit cell, nothing more than that. Okay, if you have a straight line, right, and if you have a meandered line, okay, can you tell me which line will be like lengthier compared to these two? Which one will be lengthier? Line 1 or line 2? Yeah, anyone? I have two line segments. So one is a straight line and the other one is a meandered line. Can you tell me which one will be lengthier?
The meandered line.
Yeah, totally. The meandered line will be lengthier. So now, same like idea is applied here. Instead of having a straight line here, straight, okay, instead of having a regular square loop, we have used a convoluted loop. Okay, this convolution ultimately gives us the luxury to increase the electrical length. Okay, and I have used this kind of stubs, okay, to have stability with respect to frequency response that you can like very well see from the plots that are going to follow, right? So this is a highly engineered structure, right? You can see large number of dimensions that are being mentioned here, right? So we don't want to dig deep, we just want to know like what is the actual idea here. See, we have already discussed for a 900 megahertz signal, what was the wavelength in mm, guys? For a 900 megahertz signal, what was the wavelength? Lambda equal to c by f, 3 into 10 power 8 by 9 into 10 power 8, 1 by 3. So 0.333 meters, 33.34 centimeters, or 333.4 mm for a 900 megahertz signal, right? But look at the periodicity of your structure. If you look at the size of the unit cell, the size of the unit cell is only 46 mm. Okay, I was able to reduce the size of the unit cell to be 46 mm. Okay, so is the periodicity much less than the wavelength? Yes, the unit cell size is much lesser than the wavelength. Only then this structure will provide, or this structure will give you or satisfy these two constraints or these two thumb rules for FSS design. One is polarization insensitivity, other one angular stability. Okay, right? So one is polarization insensitivity, other one angular stability. See, what are the thumb rules? Let us try to recollect the thumb rules. What are the thumb rules? So what are the thumb rules for FSS design? So number one, polarization insensitivity, and the other one angular stability. Right? So what about polarization and insensitivity? Whether you have vertically polarized, or horizontally polarized E field, you want to have the same transmission response. What about angular stability? When the angle of incidence, right? When the value of theta is either 0 degree or 15 or 30 or 45 or 60, right? Or 75. It could be in any number, okay, between 0 and 90, right? You can either have angular stability up to 45 or 60 or 75. It's up to you based on your design. You have to investigate it, right? So for different angles of incidence, I want to have the same transmission response. These are the two design rules what you have to remember. If you study any IEEE article, right? So you'll see plots with regard to these two design rules. One is polarization insensitivity, other one angular stability, right? Yeah. So see here, this is the unit cell what I have designed. Okay, instead of double square loop. In double square loop, we had some issues. We were not able to cover the required band. If you see, right, for both vertical and horizontal polarization, we were not able to cover the exact band. So using modified double square loop, I was able to address this particular issue. You can very well understand that from this particular table. Yeah. So see here, for vertical polarization, right, this structure was able to provide transmission response, okay, covering the required bandwidth. And here, with respect to horizontal polarization also, the structure was able to provide same response in the required bandwidth, right? So this is the structure what I have designed. Okay, so this is the paper substrate, right? This is the paper substrate, and copper patches I have cut and glued to the structure, right? So I did this manually. Okay, like you can also use wire cut EDM. There is a mechanical technique that is available, wire cut EDM, but this technique is like quite costly. And one more thing, this is only suitable if your workpiece is thick. I have used only 0.05 mm thick copper patches. Okay, so that is not very rigid. Okay, EDM, it is suitable only for rigid structures. Okay, it is quite hard to cut. Or what you can do, you can actually design a die. Based on the die, you can actually cut out. Uh, you can cut out these patches, okay, from your plain metal sheet. That is also possible, right? This is paper and these are all copper patches, right? So are they, can you see, they're all identical to one another, isn't it? So we tested this in the anechoic chamber, and finally I was able to get an IEEE article with the guidance what I have received from my guide, Dr. Ram Prabhu and Ram Prabhu Sivaswamy sir, and my Guruji, Dr. Gulam sir. Okay. So this was long back, probably 10 years back. Okay, so somewhere around 2016, right? 8 years back. This was the structure what we have designed. Okay, right? So we tested this in the chamber, and we are able to like convince editors like how our structure is like having a how our structure is standing a chance against articles that are available in the literature, right? So we were able to provide stable response up to 60 degrees, right? In most of the articles, if you take flexible substrates, right, they were able to provide angular stabilities up to 45-degree, right? Not now, long back, okay. We're able to achieve angular stability up to 60 degrees, right, along with the dual band operation, okay, right. So this is the like first work what I did long back, okay, probably in 2015, and it got published in 2016, okay. So I have received a lot of inputs from Dr. Gulam sir, okay, how to refine the article and how to address the like queries raised by the reviewers, okay. So he was instrumental in like drafting the entire letter. So I would like to thank him for the support what he has rendered over the period of time.
Lingesh, that's your effort. Don't give credits to me. It's your effort.
Sir, you helped us. I have to give due credits.
All right, carry on, pa.
Yeah. So now, like, so I believe I have given some insights about so how to design a frequency selective surface. What are the design parameters that are involved, right? And I have given some idea about the math that is involved. Okay, it is very essential. Only if you understand the math, you can design the structure. Okay, right? What are the different elements that are available? Okay, now let us move on to the structures what I have designed in probably uh, since 2019. Okay, right. Uh, Once again, I have given the same explanation here. Considering time, I'll skip this literature survey also. Right. So in the previous work, you have seen one flexible dielectric with one metal layer. So in this work, I have used two metal layer. Okay, so I have used two metal layer here, right? So top metal layer and bottom metal layer, and these two metal layers are connected by plated through holes on a PCB. Here I have used a rigid PCB. I call this wire as plated through hole. Okay, through electroplating, they'll create contact between top and bottom metal layers in the foundry, right? So this is the structure of the unit cell, right? So I call this as fractal inspired iterated four-legged loaded loop, right? So if you take the four-legged loaded loop, so this is the four-legged loaded loops. Okay, I have iterated this structure, right? So I have taken the inspiration from fractal. See, fractal in the sense, like if you go on zooming the structure will have the same shape, right? I'll show you a couple of fractal shapes that are available, right? If you go to fractal wiki, you can see lot of structures, right? So see here, if you go on zooming in, right, the structure will have same anatomy, right? There are a couple of structures, okay, available in the literature. This is Serpensky carpet, right? A very simple structure. This is, you can see here. So if you go on iterating the structure, right? See, fractals garnered attention in the antenna community because they have a couple of properties. One is space filling property, right? So you can increase the electrical length in the same geographical area. You can actually fill the region, right? So that is the space filling property, right? So this property is like exploited by most of the antenna designers to achieve antenna miniaturization and FSS unit cell miniaturization, right? So that is what I have done here. So instead of having a structure like this, right? So see here, so you can use a square loop, right? From the square loop, what you can do, you can come up with a fractal, you can come up with a four-legged loaded loop, right? Okay, so this is leg 1, leg 2, leg 3, leg 4, right? We call it as a loaded loop. There is a finite distance segregating these two vertical segments. That is why I call it as a loaded loop. Okay, right? So from this structure, okay, I can design a four-legged loaded loop, right? So now I can call this as iteration 1 or base structure. Then you can further iterate, right? So here in this in each quadrant, you can introduce one more four-legged loaded loop. You can interconnect them to have a larger electrical length, right? So if you consider the length of the loop, right? If you consider the length of the loop, this loop will have larger perimeter compared to this loop, right? So if you have a larger perimeter, right, you are increasing the electrical length. If you are increasing the electrical length, your electrical length, right, it is comparable to wavelength, right? So you are increasing the electrical length. Now what will happen? Your resonant frequency will decrease. That is what you see here. There is a shift from higher frequency to the lower frequency because we are actually increasing the perimeter of the loop. This perimeter is connected to the wavelength. So you are increasing the perimeter. If you increase the perimeter, automatically resonant frequency is scaled down, right? So this is iteration 1. So this is iteration 1, iteration 2, iteration 3, right? So if you go on increasing the perimeter of the loop, what do you see here? There is a shift in the resonant frequency, right? From higher band to the lower band. You are increasing the perimeter, right? You are increasing the electrical length, resulting in reduction in the resonant frequency, right? Resonant frequency is the point where you see the dip, okay, right? And what about this particular resonance? This particular resonance, okay, comes as a effect of combining the top and bottom metal layer. So this is the top metal layer, okay, unit cell corresponding to the top metal layer. This is the unit cell structure corresponding to the bottom metal layer. So if you try to interconnect, so how many plated through holes are here? Students, can you identify? This is hole 1, hole 2, 3, 4. Okay, let me use a different color here. So how many plated through holes are here? 6, 7, and 8. In each unit cell, I have used 8 plated through holes, okay, to interconnect top and bottom metal layers such that I'll be in a position to increase the electrical length in order to shift the resonant frequency. Why am I interested in shifting the resonant frequency? Because I'm designing a miniaturized unit cell. Only if I have a higher unit cell miniaturization, the structure will be more immune to varying angles of incidence, right? Okay. So here I have taken somewhere around 1 gigahertz signal. So if you take a 1 gigahertz signal, right? So what will be the value of lambda? Value of lambda once again C by F, right? So C is 3 into 10 power 8. Okay, or you can say 0.3 into 10 power 9. So 0.3 into 10 power 9 by 1 into 10 power 9. So lambda will be 1 meter. Sorry, 0.3 meters, right? Or this converts to 300 mm. I hope you all agree with me, right? So for such a 1 gigahertz signal, the value of wavelength is around 300 mm, right? Now, what is the size of the unit cell I have achieved here? The size of the unit cell is just roughly it is 10 mm, right? So compare the size of the unit cell is close to 10 mm. The actual wavelength is around 300 mm, right? So you can compare these two, right? 10 mm by 300 mm. What will be the outcome? 1 by 30, right? So I was able to reduce the size of the unit cell to somewhere around lambda by 30, right? Okay, that is the amount of miniaturization what I have achieved with this kind of unit cell, right? I have top and bottom metal layers that are interconnected by plated through holes. With the help of these plated through holes, I was able to achieve connectivity between top and bottom metal layer, resulting in increased electrical length, shifting the resonance from higher band to the lower band. Clear? What is the idea behind fractal? Here I have used two concepts. One is fractal, other one plated through hole. Okay. So see here, using the idea inspired from fractals, I was able to increase the perimeter. So this is with respect to top metal layer. Similarly, in the bottom metal layer, I can have one more identical unit cell, but I want to interconnect the unit cell at the top and bottom through metallic vias, nothing but plated through holes, such that I'll have increased electrical length. Okay, right? So you can very well see here, if you use a square loop, the perimeter was around only 38 mm. Then between this square loop and iteration 1, right, there is no change in the perimeter, but there is change in the resonance. That is quite explainable, because we have changed the unit cell structure. The amount of coupling between the unit cells would have changed, leading to shift in the resonant frequency, right? And look at iteration 2. I was able to increase the perimeter by at least, probably if this is around 40, right, at least twice. Okay, more than twice, 2x increase in perimeter. Okay, loop perimeter. Then compared to square loop, what about iteration 3? This 40, this close to 170, right? More than 4 times. And what about the proposed loop? In the proposed loop, I have two metal layers. Try to understand, you have two metal layers. These two metal layers have the metallic pattern similar to this. Okay, right? The yellow one, this is the dielectric substrate, FR4. Right? And the darker one, this is the metal layer. Okay, we have metallic patterns like this. Right? So if I go on increasing the iteration, I can very well see there is an increase in loop perimeter, right? Till iteration 3. Can you see here? So with fractals, right, with the idea inspired from fractal, okay, I can increase the loop perimeter from 38 mm to 173 mm. Then what I did, I had two metal layers. I interconnected these two metal layers with plated through holes. Once I do that, once I do that, I was able to increase the loop perimeter by a factor of 2, right? Here it is somewhere around 180. It is more than 360, isn't it? Okay, here till from square loop to iteration 3, I have taken the inspiration from fractal. Then from iteration 3 to the proposed loop, I have used plated through holes to interconnect top and bottom metal layers, okay, in order to increase the electrical length, such that I achieve unit cell miniaturization. Along with that, okay, angular stability will come into picture. Anyhow, the compromise will come in terms of bandwidth. Okay, right? So see here, this is what I have mentioned, close to 30, right? You can recollect here. For a 1 gigahertz signal, okay, what is the value of lambda? Value of lambda is around 300 mm. Now, what is the size of the unit cell? Size of the unit cell is just 10 mm, right? So 300 by 30, you'll get 10. I was able to reduce the size of the unit cell to somewhere around lambda by 30. That is the beauty, right? I need only 1/30th of the wavelength. Okay, the unit cell size will be only 1/30th of the wavelength. Right? So once again, same plots. You can see somewhere around 1.056. That is the resonant frequency. Okay. So this is used in distance measuring equipment and tactical air navigation. Okay, basically radar. So I handled a course on radar. So that is how I got inspired to work in this particular band, distance measuring equipment and tactical air navigation. Okay, right. So this is the plot of shielding effectiveness. You can see for different angles of incidence, there is a consistency in the resonant frequency. Okay, this is with respect to TE mode, nothing but TE mode refers to your vertically polarized E field. Okay, and what about TM mode? TM mode refers to your horizontally polarized E field. Okay, once again, for different angles of incidence, I'm able to achieve the same transmission response, right? So this is the surface current distribution on the unit cell for vertically polarized E field, right? So we have a like facility available at SSN. Okay, so you can look at the grid of rectangular grid of observers. Okay, where you have a housing. So in this housing, so we have placed the frequency selective surface. So this is a 1 feet cross 1 feet structure, right? So we had 30 unit cells along X and along Y we had 30 such unit cells, right? So 30 by 30, somewhere around we had more than 900 unit cells. Okay, so this is a 1 feet cross 1 feet structure. Okay, close to 1 feet cross 1 feet structure, right? So between a pair of transmitting and receiving horn, we have actually placed this structure, and these two horns are connected to a vector network analyzer, and we were able to get the measured results. Anyhow, measured results they'll somehow deviate from the simulated ones. There are a lot of reasons for that. Okay, right. So I did a comparison between the structures that are available in the literature and the proposed work. So I was able to bring the unit cell dimension to 0.034 lambda naught, probably lambda close to lambda by 29. Okay, so this was the resonant frequency. I have used a FR4 substrate with a dielectric constant of 4.3 and height of the substrate 1.6 mm. And the angular stability I was able to achieve around 75 degree. Okay, maximum angle 75 degree, right? So this is the summary, right? The targeted frequency was 1.056, right? So I was able to achieve a peak shielding effectiveness of 24 dB, right? Bandwidth 100 megahertz. The structure was polarization insensitive, offering same transmission response for transverse electric and transverse magnetic modes of incident electric field, right? This is nothing but your vertically polarized E field. This is nothing but your horizontally polarized incident E field. And angular stability, I was able to achieve 75 degree. What about figure of merit? Figure of merit, like lambda naught by P, this lowercase p, okay, uppercase P generally represents power, lowercase p, it is periodicity. I was able to achieve 29. And what about the miniaturization? This is just an inverse. Okay, if you find the inverse, this is what you will get. Okay, 0.034 lambda naught. That is the kind of miniaturization I was able to achieve, right? Okay. So what about the application? We like this is what I have mentioned. Okay, tactical air navigation and DME. So now in most of the systems you have GPS. Okay, if you take aircrafts, so you have GPS. But whenever GPS is not available as a fallback system, in some of the airports and uh, carriers, you can see DME and TACAN. Okay, this was the targeted band, right? We were able to achieve 100 megahertz band covering these two, right? So there is one of the works what I did for my PhD, and this is the another work, right? So how many of you are using Wi-Fi at your homes? Every one of you, right? I believe I'm audible to you. Yes? So how many of you are using Wi-Fi at your home? Everyone. Everyone does, right? So what are the bands in which Wi-Fi is functional? So now you see most of your laptops and mobile phones coming out with Wi-Fi 7. Okay, so there was a drastic jump from Wi-Fi 6 to Wi-Fi 6E. Okay, Wi-Fi 6E we call it as extended Wi-Fi 6. Nothing but, so why in if you take Wi-Fi, they generally operate in these two bands, 2.4 and 5 gigahertz band. Okay, right. In Wi-Fi 6E, they extended the band up to 7.125 gigahertz. Okay, right. So here we have targeted 2.4. Okay, 2.4. This is basically an ISM band. You very well know. You don't need any license to operate in this band. Bluetooth, Wi-Fi. Okay, they both operate in this particular band, right? Yeah, I guess I can move on. So this is the unit cell structure. You can see the yellowish one. This is the dielectric substrate FR4, and the red pattern. This basically represents your metal layer. Okay. So here, this is the interdigitated loop element. Okay, what I have utilized to design a miniaturized unit cell, right? So this is a 3 by 3 array, right? Right. You can see 3 times the periodicity of the unit cell. So this is, let me draw the clear. Let me draw the. So this is one unit cell. This is another. This is another. Okay, similarly, you can see there are 9 unit cells forming a 3 by 3 array, right? So let us take Wi-Fi signal, right? Somewhere around 2.4 gigahertz. What will be the wavelength for this particular signal? So lambda will be C by F. So if you do a simple math, right? So let me take a calculator here, right? So zero point 0.3 into 10 power 9 divided by 2.4, right? So it is around 125 mm. The size of the, like, the wavelength corresponding to 2.4 gigahertz is around 125 mm. But look at the size of the unit cell. The size of the unit cell is just 6.25 mm, right? You can very well see to what extent I was able to miniaturize the unit cell. Okay, right? So see here, there are a few geometrical parameters I have introduced here. P is periodicity, right? So periodicity of the unit cell is 6.25 mm, and S is the strip width. Okay, you can see strip, right? This strip width is around 0.1254 mm, nothing but 6 mils, right? You can do a small math here. Okay, right? Mils to mm conversion, right? So it is simply 6 mils, right? 0.1524 mm. And once again, G is the inter-unit cell distance. Say I have unit cell 1 and unit cell 2. They are separated by this particular unit cell distance, distance G, right? Yeah, let us try to recollect what are the thumb rules, whatever we have studied. Whenever we want to design a frequency selective surface, these are the two design rules we need to satisfy: polarization insensitivity and angular stability, right? For different polarizations, for example, vertically polarized and horizontally polarized E field, I want same transmission response, nothing but for TE and TM mode, I want same transmission response. Okay, I believe this makes sense, right? So no matter whatever be the angle of incidence, once again I want same transmission response. Okay, so now let us bounce back to our discussion. So see here, I did a couple of parameter sweeps to understand how does the structure uh, resonate to the incoming electromagnetic energy, right? So if I use different dielectric heights, right? I have used a FR4 as a dielectric material. If I use different dielectric heights, right, for different thicknesses, what about the response, frequency response? Right? So there is a small shift in the curves, but it is not so predominant. Okay. Now, what about change in periodicity? If I change the size of the unit cell, I can very well see there is a shift, right? What about the transmission response for both TE mode, right? For both TE mode and TM mode, I can see a dip at 2.4, indicating the fact that this structure can provide shielding against Wi-Fi signals that are centered around 2.45 actually. Okay, clear? So here, what about the amount of attenuation? 90% attenuation, or I can say 90% of the incident power is reflected back. Only 10% of the incident power is reaching your receiving antenna from transmitting antenna. What about angular stability? Once again, if you look at the angular stability at 2.4, I can see the structure is, the response is quite consistent, indicating the fact that the structure is immune to different angles of incidence of the incident E field. Okay, with respect to T and TM, right? So this is the surface current distribution on the structure, and I derived an equivalent circuit model. Maybe for undergraduates, this will be quite tough to understand. Okay, maybe I can give you small idea about this. So whenever you have a metallic grating like this, for the vertically polarized E field, this will act like a inductor. Okay, and whenever you have a horizontal grating, okay, for vertical metal strips, for the vertically polarized E field, this will act as an inductor. And if you have a horizontal grating like this, and for the vertically polarized E field, this will behave like a capacitor. So this is an inductor, this is a capacitor. Okay, that is the idea I have used. Then from the geometry, with the help of literature, okay, I did a lot of math. I used MATLAB along with Keysight, ADS. Okay, there are a couple of equations that are involved. Okay, I'm going to skip this. So with the help of these equations, I was able to find out, okay, what will be the inductance and capacitance. Then using Keysight ADS through repeated simulations, I was able to find out what will be the value of resistance. But there is no guarantee that these values will be quite real. Okay, this comes all because of the resistive nature of your metal. Okay, so this is the comparison between the equivalent circuit model what we have derived and from the structure what we have simulated with the help of CST Microwave Studio, right? So from the structure we got the response. Then this structure is converted into an equivalent circuit with a resistor, inductor, and a capacitor. I have converted the structure into a simple RLC circuit. Then from the RLC circuit, I try to figure out what will be the transmission response. This is actually shielding effectiveness. Okay, right? Nothing but minus of S21 in dB. You can see like more than 10 dB shielding effectiveness at 2.4 gigahertz. And you can see high degree of coherence between like the curves that are obtained from CST Microwave Studio and the curves obtained from equivalent circuit model for T and TM modes, right? Then we did experimental investigation also, right? We fabricated the frequency selective surface. We tested it in an anechoic chamber to figure out like what is the coherence between simulated and measured results. Okay, so anyhow, I didn't fake any of the results. Whatever I have obtained, okay, I have put it on the paper. and the editors, they were so generous to accept accept the entire work. Okay, so I don't want to dig deep, right? So a small comparison here, right? So if you look at the articles that are available in the literature, in one work they have used even a unit cell size much lesser than what I have proposed. But in one unit cell they have used 64 vias, but I reduced it. Okay, but in this work I reduced it to nil. Okay, without any such via, I was able to achieve this. But this is a dual band structure. This is a single band structure. It is not actually righteous to compare these two. Okay, but if you are only interested in 2.4 gigahertz shielding, this could be one of your options. Okay, right? So the angular stability I have achieved close to 75 degrees. So the only novelty in this structure, we have used interdigitated structure. Okay, right? So this is an interdigitated structure, and I was able to extract L and C values. Okay, using a couple of equations that have appeared right from 1950. There is a textbook called Waveguide Handbook that has appeared somewhere in 1950 or 55. Lot of enhancements happened to these equations, but I went to the roots to figure out how these equations have evolved over the period of time. Then I understood. I did a lot of simulations with MATLAB, Keysight's ADS, and finally I was able to figure out how to use these equations for my structure and derive LNC values. Okay, so that is the kind of work what I did. Okay, for my PhD. So this is a quick summary. So resonant frequency 2.4, shielding effectiveness somewhere around 40 dB, right? The structure was polarization insensitive. I achieved angular stability up to 75 degrees. Figure of merit, so up to 20. So lambda by 20, right? So lambda by 20, you can very well see 0.05 lambda naught. That is the miniaturization what I have achieved. Okay, and 10 dB shielding effectiveness bandwidth. You can see the entire 2.4 gigahertz band I was able to shield. Okay, right. So these are the publications, and I would like to show a couple of publications that have come out. So this is the first publication. Okay, somewhere in 2016, and the other one. So this was in 2021. Okay, with respect to, I got this in IEEE transactions on electromagnetic compatibility, and the other one on Wi-Fi. So this is on IEEE transactions on consumer electronics. Okay, so this is the entire, and we have also discussed a use case in Wi-Fi 6 dense deployment. Okay, how this can save power. Okay, that is the use case. Yeah, I guess like I'm done with this presentation. Now I'm open to take questions from you.
Good evening, sir.
Yeah,
So I have an interesting presentation from the start to end. So
yeah,
I have some doubts regarding the design and characteristics of FSS.
yeah, yeah.
So for unit cell design, I can understand that you have fixed the periodicity for the miniaturized size.
Yeah.
So what about the resonators? So is there is any formula for designing those resonators or
Yeah,
uh,
like for basic structures, a couple of equations are there, but there are no straightforward equations when it comes to FSS design. For like if you take microstrip patch antennas, there are a couple of calculators. There are if you take EM talk patch calculator, so this is available for antenna design. But with regard to FSS, uh, like we don't see any. So what we did, we created one such. Okay, so you can see there is also indexed by square loop FSS calculator. We have created a calculator